All right, great questions. I'm really sorry we had to cut them off, but again, please feel free to bring them up with our speakers during the breaks. And thank you, Prakash, for sharing your insights on how to successfully build AI within such a large organization like Petronas. So please allow me to introduce our next speaker, Wojciech Matusik, who is a professor of electrical engineering and computer science here at MIT CSAIL. He leads the computational design and fabrication group and is also a member of the computer graphics group. Wojciech is the co-founder and CTO at Inkbit, and he also holds more than 40 US patents. So please join me in welcoming Wojciech to the stage.
Thank you very much. Thank you very much for the introduction. So I will be talking about how can AI help us in design manufacturing. First, I would like to tell you that, of course, design is everywhere. So for a mechanical engineer, that will be a design of this beautiful car. If you are talking to a chemical engineer, this will be a design of novel molecule systems. If you are talking to a computer scientist and computer engineer, that will be a design of new algorithms. If you are talking to an architect at NVIDIA, that will be designing of an AI chip or a chip that is used in high performance computation. So as you can see, design is everywhere. I think it's really it touches our lives in every possible aspect. I would say that most of this work that we do here at MIT is actually design. So most of the folks, I think, at MIT, I would say, are involved in some form of design. I have been working on specifically on being able to build machines that use AI in design manufacturing. This particular machine uses computer vision to be able to self-correct and be able to understand what's going on in terms of the process. So what is really amazing about these types of new digital machines that are emerging is that they can start automatically make almost anything. So for example, this is directly 3D printed part from this particular 3D printing machine. It uses a number of different materials internally. As you can see, I can just design this particular file for this robot, send it to the machine, comes out completely automatically done. And it was going to work, sense, interact with the environment. So this is just the beginning. We live in the area of automated manufacturing where we will see completely automatic ways of design and manufacturing things. The problem with this particular aspect, what really is perplexing me, is that it took 2 or 3 months for a highly skilled of digital designers to actually design this file. So while manufacturing was almost instant, it took pretty much 1 afternoon to build this robot. Designing this robot took much, much longer. So the question that we would like to really attack right now is really how can AI methods help us in designing and manufacturing these objects? Obviously, this is a very, very difficult topic, and this is very, very challenging process. So I would like to break this into a number of questions. And so let's take it step by step. The questions are, how do we represent design? That's question number 2. Second question is, how do you represent and learn design spaces? Third, how do we find designs with optimal performance? The last important question is, how can large language models help us in design and manufacturing? And I think this is something that probably many people really care about these days. All right, so how do we represent designs? We looked at this quite a lot from many different angles. And what I really find, I think one of the most general representations for the designs are graphs. Pretty much, if you take any graph, you can represent, if you take any design, you can represent it with any graph. So for example, if you take architected material, if you take a molecule, if you take a robot, all of these things can be represented using graphs. That's very, very important. So let me give you an example. For example, if you take a molecule, in this case, you can imagine each atom is going to be a node in the graph. The bonds are going to be edges between the graphs. As you can see, we can build completely digital representation of this physical entity. And of course, these graphs can be multi-scale. can have multiple scales. They can be annotated with continuous parameters. But at the very, very heart, these are going to be graphs. What's really important here is graphs can be represented using a text. So there's a very, very direct translation between any graph representation and text. Second question, how do you represent and learn, how we represent and learn design spaces? So first question is, what are design spaces? Design spaces, you can think of design spaces as a family of designs. It's not a single design, but a family of designs in a given category. And these can be very, very specialized. For example, if I take polyurethane, this is a class of chemistry. I can say, this is a class of designs, molecules that I would like to represent. So there are obviously many, many different representations for design spaces. The particular one that I like is using formal languages. So languages very, very similar to what we use in computer science. And typically these languages have terminal symbols. You can think of these the end parts. They have non-terminals. You can think of these assemblies of things. And they also have rules. Rules convert parts of the designs, non-terminals, into potentially non-terminals and terminal symbols. And the idea here is that you can start with very small number of rules, relatively small number of terminals, and you can start with the so-called start symbol, and you can do the so-called rewrites, or you can kind of expand this and create a given design. At the end, as you can see, after the series of these expansions, I have a design, I have essentially a program, and I can and I have a graph, right? And I can pretty much have the corresponding physical thing. So this is a very, very compact way of representing design spaces. Small number of rules basically allows you to really build potentially millions, if not billions, of different designs in a given specific category. Very important part. These graph grammars and these language representations are naturally text. This is all text. Very important. We are going to come back to this later. So, for example, I had my students build these specialized representations, for example, for many different disciplines. For example, they started with chemistry. You can take any class of chemistry, you can put a graduate student on this, and they will build you a beautiful representation. For example, if you want to work with polyurethanes, 14 different rules allows you to express all of the different polyurethanes in the class. If you want to look on complex UAV systems, you can design very similar grammars for expressing different types of complex UAVs that have fixed wings, rotors, and so on. Again, we have done this, built lots of different UAVs. As you can see, once you have the grammar, you can start this kind of representation. You can then sample and create many different topologies that you can imagine. We have done the same thing for architect materials or meta materials. Pretty much very similar structure and very similar representations can be used to represent pretty much any type of material you can imagine. So you can see, these are all of the individual different types of meta materials. And as you can see, there's underneath each one, there's a little program, there's a little graph that tells you how the program is constructed. And using this simple representations, very, very compact programs, you can pretty much expand this to any existing metamaterial you want. So for example, we have taken all different types of metamaterials in the literature, and we constructed the corresponding programs for this design. And once you understand that you have the right coverage, right, you then express everything that people have done in the literature. Well, of course, you can also then start sampling new types of programs, and you're going to start generating designs that nobody has ever seen before. And of course, these kind of samplers can do that. So this is basically, this requires for you to construct these languages by hand. The obvious problem here is that in order to do this, you have to put a domain expert and a computer scientist in one room. And this is kind of very, very difficult to do that. So the question here is, can we somehow synthesize these languages automatically? And this is what we have been doing so far. So the idea is as follows. I'll give you a set of examples of given designs, a very small set of examples. Let's say I give you 20 different designs. And now I would like to construct this language automatically. So in fact, we can do this. So using small set of designs, we can pretty much synthesize these grammars automatically. The idea here is essentially that you are going to take the designs, all of these graphs, you are going to start collapsing the edges. In the process of collapsing the edges, you are going to essentially create the rules for the grammar. And there's essentially, you can do it in a very, very principled manner. In fact, you can pose this as optimization problem. So pretty much this grammar construction or this language construction can be posed as an optimization problem. And this is very, very nice, because basically then you can throw at it all of the existing optimization methods and you can recover this. So this is nice. Using small set of examples, we can now construct these languages automatically. Right, so these are the first questions: how you create the design, how you represent design, how you represent design spaces. Let me talk about the third one. The third one is something that engineers really care about, and that's basically the performance. So typically in engineering, we don't necessarily only care about the structure, but we also care about the property. What does it mean? Basically, we care about not only about the design, but the behavior or the performance of the given design. So in order really to attack this problem, you have to have two things. First, you have to have the generative model, and these languages can be used as a generative model. And these languages essentially they can create millions or however many designs you want for you, but you also need to have a predictive model. Predictive model is going to take each of the design and is going to compute this underlying performance. So you have to have both of these models work in tandem. And in fact, what we have sort of shown that you can learn these models directly from data from very small set of examples. So that's kind of very, very important. Small number of examples, and I can still both build a generative model that expands my original data sets from small to many. And then for each of the designs that we are going to synthesize, it's going to also synthesize the performance. Naturally, if you have these two metrics, you can enumerate all of your designs. You can also synthesize the performance, or you can compute the performance of the design, and then you can select the best possible designs. In fact, we couple it with something that's called differentiable physics. So for example, in this case, we have differential simulation system. So let's imagine I would like to build a drone with optimal performance. Pretty much, if you want to automatically synthesize both the shape of the drone and the corresponding control. So these systems are going to be also used to adapt the design and also adapt the code that runs the drone. So in this case, as you can see, this is a vertical takeoff drone transitioning to the flight and then a landing. So these systems allow you to synthesize not only the shape, but also control very, very efficiently. And we actually flew these drones. So actually, this is not just a digital simulation, but you can fly those as well. So let me go to the last question. So everybody that sort of works in design and manufacturing think about this: how this new wave of large language models can really help us in design and manufacturing. And this is really, really interesting because we've seen so many nice examples of creating amazing new images, but they kind of stay very much in the entertainment space. How can we bring all of this stuff back to design engineering? And there's a really interesting part that I was already talking to you about. All of the stuff that the designs in designs and all of the manufacturing data is extremely structured, can be represented using text. So that's very, very important. This is naturally very, very compatible with all large language models that we have. So how are the future design and manufacturing ecosystems are going to look like? Today, they are really a combinations. This is like almost many, many different types of apps that work together, right? You have parametric design, simulation optimization, documentation, design for manufacturing, CAM, part sourcing, and so on. These are all different. There are different apps that are sort of responsible for each of these pieces. And typically, you have the user. A user, typically, or a team of people, pretty much interact with all of those. So the interesting part is that now we are going to see sort of co-pilots that are going to be helping users in this design and manufacturing process. And I think this is going to be very, very important, as it's going to really heavily increase our productivity. So we have done initial studies how we can potentially do this. And what is really interesting that, for example, all of the designs, as I said, are text-based designs. They are written in all very specific CAD systems. And you can pretty much say something like this, I would like to build a cabinet with these kind of specifications. Please synthesize me a program that sort of I can run in our CAD system to synthesize this cabinet. So using pretty much off-the-shelf models such as GPT-4, we can start synthesizing these designs. You can also give a program that corresponds to a given design, and you can sort of say, I would like to expose the parameters of this design. I would like to figure out what the right bounds for these are, and the system automatically is going to parse this program, figure out what the right parameters are, what are the particular bounds for each of those. You can also optimize the design. So for example, if I say something relatively simple, I would like to optimize the cost of this design. I would like to maximize the volume. The system will know exactly what type of function call should I call to the optimization call to optimization packages that basically would allow me to optimize this given design. And of course, a system like this allows you to also do part sourcing. It will allow you to call the right libraries for to cut or manufacture the parts. And so you can of course, design the right assembly instructions and so on. Another example, a little bit more difficult. Let's build a quadcopter. I would like to build a quadcopter. It's basically sourcing the right parts, components, figures out what are the most interesting components applicable components that we should use there. And then we can, of course, do manufacturing assembly, generate the STL file, generate assembly instructions, and assemble the final piece. And of course, we can try and test it, and hope, of course, it runs as well. So there's really interesting sort of, question, given these very preliminary versions of these systems built using off-the-shelf components, how, where will it go? And I think it's going to be very, very interesting. The next few years are going to be really fascinating for design and manufacturing. And really the interesting part is, how do you want to build the future design ecosystem? So I think the important part is really to be able to translate all of our data, design manufacturing data, to structured formats. So today, we already started building these specialized domain-specific languages, for example, for CAD and so on, but there's so many others that needs to be much more structured and adapted and used. Then the second important part is really, how do you really develop custom and enterprise-specific large language models? The design manufacturing data typically, is not going to be really shared across many enterprises. This is a very guarded data that nobody really wants to really share with others. So it's really important. How do you really build large language models that are specific to each organization? And then finally, I think the important part is really, how do you build an integrated AI copilot solution that's going to be really be used to integrate all of the different parts of the design and manufacturing ecosystem. So what are the benefits here? There are lots of opportunities, and I think they are very, very important. So first, the important part is that we can reduce overall the product development times. You can drastically shrink how long it takes to develop a given product. At the same time, of course, we will be shrinking the overall cost of the developing products. We are going to improve product quality. Now the designers and engineers will be able to explore more options. So ideally, they will be also improve the quality of the product. We also are going to potentially increase the workforce productivity using the co-pilots. A given person will be able to do the task in a fraction of time that it takes them today. We will therefore reduce significantly R&D costs, and of course we are going to increase workforce engagements. There are particular parts of the tasks that are very boring, mundane, and these are the parts that need to be really improved and so potentially eliminated. What are the challenges? There are many challenges for deploying these kind of solutions within a given enterprise, and these are as follows. So there's typically a very limited internal knowledge of how to build a solution like this within each enterprise. Then create this a very complex large data sets for design manufacturing is obviously very challenging. We do not have data. Maybe data is scattered and hidden throughout the whole organization. Typically, this needs to be collected even within a single organization. We need to also develop formats for structured and semi-structured data. So if you can develop these formats, learning is going to be much easier. This is very important, right? Because less data or being able to less with fewer data points is going to really improve the behavior of the system. We also have to be able to deal with a large data variety. If you look at different types of documentations that we have today, there's probably 30 or 40 different types of documentations that given organization uses. This is very challenging to really be able to support all of that. And then finally, I think it's very important to build large language models that are less expensive to train and execute. And I think while training, maybe that's fine. And of course, the industry is really moving forward. Being able to execute them really for each person in the organization is going to be challenging, right? If all of these models run on expensive GPUs, right, that's going to be challenging. But of course, the whole industry really is really working on making this solution very tractable. All right, so these are my conclusions for the talk. I really think generative AI tools and machine learning tools are here to stay, and they can really help organizations in improving their operations. I think it's also important to note that design and manufacturing data is very structured. This is all tables, text, programs. Essentially, sometimes they are not exposed, but they can be all structured as text, and they can be really very compatible with existing large language models. And our group is really developing new tools, new generative AI copilots that is used for design manufacturing. This is really what we are passionate about, and this is what we would like to push. With this, I would like to end. Thank you very much. Any questions?
When you were building the models, did you find designs that came out that the designer didn't have a concept of, like new structures? So I just kind of talked through what came out.
Absolutely. I think this is a very interesting question, right? And really this means, the question really, I think, means, can I build something that I haven't seen before? And it's very tricky, because typically machine learning models are not very good at extrapolation. So they are really good, if you have a design A and design B, basically it's going to give you a cross between A and B, right? So it's going to be some components of A, some components of B. The interesting part about, so extrapolation is hard, okay? The interesting part about the types of methods that we are developing is that pretty much you take a design and you start decomposing them into pieces, okay? So you are taking the design and basically these methods essentially take the design and sort of start breaking them up into components, and then creating the rules how you really can connect these components. And then you pretty much can take a combinations. You can think almost this, you have a design A that's made of some Legos, and then you have design B that also is almost out of some Legos. You start basically decomposing it and figuring out what these Legos blocks are and how to connect them together. And then you can sort of start recombining the Legos in some new ways. So in a way, you can start designing things that are composed of these Legos, but you cannot really come up with a new Lego block Okay, so if there is some subcomponents that was not in the original data set, that wasn't really there, these machine learning models are not going to invent a new Lego block for you. That's basically the, and I have to sort of say that this is very, very interesting because many innovation happens, or like many innovations happen when you kind of have a huge, increase in productivity or in performance, and this is because something new is brought to the table. Some new, completely new component came to the table. Let's imagine like a jet engine. Before basically invention of the jet engine, you could sort of combine different elements of the planes, and you would basically get some new plane, right? But the invention of the jet engine pushed, what the planes can do today. So what I'm trying to say, that these machine learning models are unlikely to invent a jet engine for you, right? But they will be able to pretty much recombine existing components of the standard planes. So I think this is very, I think the next phase of AI is going to be, can these models start inventing the jet engine or new components of the blocks?
Hi, so I had a question. So earlier in the talk, you mentioned about how you can model materials and designs using graph and graph grammar. So later then you showed how you can use ChatGPT to like build a cabinet. So was ChatGPT using the graph grammar, or was it using like some other like documentation?
So in this particular case, the ChatGPT was using a programming language. You can think of the programming language as a grammar. All of the current programming languages essentially are in a form of grammars, basically a form of formal languages. So in this case, right, we already use, so GPT already knows about these languages. So we didn't even have to teach GPT all of these languages. It was able to pretty much bring it already understands these languages and is able to synthesize it. If you actually have you have very specialized languages constructed using graph grammars, you can actually feed them directly to ChatGPT and say, this is my grammar, please synthesize a design for me that actually is expressed using this grammar, and it's going to do it for you. Yes. All right, thank you.